The dream of fast and efficient flight without the need for runways has proven one of the toughest technological nuts to crack in the history of aircraft design. Despite a century of efforts, some featuring truly spectacular engineering, vertical takeoff and landing aircraft remain perhaps the best example of how there is no such thing as a free launch in aircraft design. We are still at the stage of vertical takeoff, efficient cruise, high speed, pick two. But in the 1950s, Lockheed believed that they could have their cake and eat it, and the result was the XFV-1. The vision, a sleek, agile, fast fighter that only needed a ship's helipad to take off from. And it looked great on paper. Then it looked fine in the lab and in the wind tunnel, but then with a full-scale prototype finally in the air, it all sort of unraveled. In this video we look at what went wrong and whether, from the perspective of the current age of digital control systems and of the huge interest in electric VTOL, was the idea of the XFV-1 fundamentally sound, just 70 years too early? And to help understand this, we go back to first principles on powered lift, and we fly in two machines featuring the same power output, but very different ways of slipping the surly bonds of Earth. The early 1940s saw some heroic feats from US Navy sailors as they were fighting to protect merchant ship convoys in the North Atlantic. After the war, however, the threats changed, and so did the focus of the US Navy, now adopting a more offensive, more power projection stance. But while resources for its convoy protection role dwindled, the potential threat to shipping did not disappear, this time expected to come from the Soviet Navy instead of German U-boats. The US Navy's Bureau of Aeronautics came up with the exciting idea that ships could be equipped with turboprop powered, we're in the early 50s, turboprops were the flavor of the month, fixed-wing fighters to defend them, launched from and recovered to their decks, operating as mini aircraft carriers. Except, unlike ordinary aircraft carriers, these vessels would only have enough deck space to swing the ship's cat. So, absent a runway, the aircraft would have to sit on its tail and launch into a prop-hanging climb from the deck, as well as land in the same way, sort of reversing down from a prop hang. And with nobody able to think of a single way in which any of this could possibly go wrong, a requirement was drafted and a competition launched. 5 companies put in bids, and courtesy of a chap called Jared A. Zicek, who recently documented each candidate in a series of beautiful illustrated books, which I'd warmly recommend, we can now get a sense of the diversity of concepts that resulted. And no, they are not hallucinations of an early generative AI model. Goodyear, Martin, Convair, Northrop and Lockheed really did some out of the wing box thinking here. In the end, Lockheed and Convair were invited to develop flying demonstrators, which they did. Now, the somewhat improbable looking Convair ended up being able to demonstrate more of the required mission profile before both programs were cancelled. But I'm going to focus on the Lockheed entry because the sole completed XFV-1 demonstrator prototype actually survives to this day and can be visited, which I was lucky enough to be able to do in the lovely Florida Air Museum in Lakeland. Do go if you can, worth it for a million reasons. They have some real gems, including a contemporary alternative vision of naval air power without a runway, the incredible Convair Sea Dart. Why not just drop one of these off a ship when needed? Anyway, I'm digressing here. On to the XFV-1 then. Let's talk basic geometry. It stands 11.4 meters tall, or long if you'd like, with its 8.38 meter span wings featuring a very slight quarter chord sweep, looking somewhat stubby with an aspect ratio of just over 3. Their total projected area of 22.9 meters squared and a maximum takeoff weight of just over 5.8 tons results in a wing loading of around 2.5 kilopascal. Not unusual for fighters of the era, perhaps on the lighter side, though this was just the weight of the prototype. An interesting trade-off there, no doubt. Higher wing loading makes for a more difficult transition to horizontal flight, but improves the chances of a safe deck landing on a day with variable direction winds. The forward-swept trailing edges hold full-length flaperons. The XFV-1 sits on a cruciform tail set in an interdigitated arrangement. I've been waiting for ages to work that into a sentence, meaning that the wings fall between the fins in the front view. There are full-length rudder vators on each fin, and of course their pitch authority was extremely important in terms of making the transition happen. In general, with next to no legacy knowledge on the control and handling of a transitioning vehicle, questions like what the control surfaces should look like had to be answered in scale model tests. And several test rigs were built at scales from 1 to 10 to 1 to 4, most of them powered, since prop wash was clearly going to play a major role in the effectiveness of the controls. Building such things with 1950s control motor and battery technology was non-trivial, and some rather complex tethered rigs had to be built, first to test takeoff and landing with separate pilots looking after the 3 control axes, and further operators needed to manipulate the power and the safety cable designed to rescue the model in case things got out of hand, or 8 hands in this case. Further tests looked at transition maneuvers, which were quite aggressive as they had to be completed quickly, in 21 seconds on takeoff. More on this shortly. These tests required transverse airflow, so of course the whole one pilot for each degree of freedom setup had to be run inside the NASA Langley wind tunnel. The performance requirements of the XFV-1 did not lack ambition either. The production aircraft was to ultimately carry 4 20mm cannons with 150 rounds each, as well as a radar to a staggering 45,000 feet, reaching 35,000 feet in 4.5 minutes. But the most striking number of all was the target maximum Mach number of 0.94. Was this really possible with a somewhat stubby aircraft with large pods on the ends of nearly straight wings and a rather complicated tail with little shopping trolley wheels on the tips? A 1 in 10 scale model was built and extensively tested in the 12-foot pressure tunnel at NASA Ames, with a scale replica of the actual propellers driven by a pair of water-cooled 36 horsepower electric motors. The model propeller blades could be bolted on at various angles, allowing the engineers to simulate the variable pitch prop of the real aircraft. The tunnel was run all the way up to Mach 0.92, just short of the targeted peak Mach number of the aircraft, and the results were much as you would expect. A nice, slippery minimum drag coefficient of about 0.02 at Mach 0.5. These are all with propellers removed. A nice, slippery, also 0.02 at Mach 0.7, 0.023 at Mach 0.8, and then, oh wait, here comes drag divergence at Mach 0.85 with 0.03, Mach 0.9 with a rather robust CDmin of 0.042, and around 0.05 at the tunnel top speed of Mach 0.92. A crunchy 2.5 times the value recorded at 0.7, which, while probably not unexpected, would certainly have given the engineers food for thought in terms of how tough those last few hundredths of the target Mach number were going to be. The other term of the speed equation is, of course, the thrust required, and Lockheed opted for a helicopter-style twin-turbine arrangement with an Allison XT40A unit consisting of two Allison T38s, driving a pair of contra-rotating propellers through a common gearbox. The idea of turboprops operating at 0.9-ish Mach numbers feels somewhat outlandish today, but at roughly the same time as the development of the XFV-1, McDonnell were working on their Mach 0.9 XF-88B Voodoo, powered by the same Allison T38 Lockheed were looking at, used as a sort of thrust augmentation unit, supplementing its two afterburning Westinghouse J34 turbojets. What an extraordinary age of experimentation the 1950s were. So, assuming the XT40 would supply the high altitude power required to push through the massive drag rise at around Mach 0.8, leaves us with the question of how much power would the XFV-1 need to make the vertical takeoff element of the mission profile work. The amount of power required for VTOL is a somewhat complicated and in some ways counterintuitive issue, and it is perhaps illuminating to consider it by starting from the power requirements of the most conventional VTOL design options, helicopters. In fact, let us compare the flight performance of a helicopter with that of a fixed-wing aircraft equipped with the same total propulsive power. There were plenty of helicopters in military use at the time of the Lockheed XFV-1, from the very light, the Bell 47 of MASH fame, to the heavy lift, for example, the 14-ton Sikorsky CH-37. But for reasons of convenience, let us consider this rotary versus fixed wing same power comparison from a modern-day perspective.
This is a Robinson R66. It has a maximum takeoff weight of just over 1.2 tons, and it is powered by a single Rolls-Royce RR300 engine, the latest descendant of a long line of Allison Model 250 free-turbine turboshaft engines. This here is an earlier Mark. As the designation suggests, it is capable of 300 shaft horsepower, but in the R66 it is derated to 270 shaft horsepower. It has a gas generator spinning at over 50,000 rpm and an output shaft speed of around 6,000 rpm, reduced by a gearbox to 410 rpm on the main rotor. The starting point of our discussion being a proposed VTOL fighter aircraft, no comparison of VTOL architectures is complete without comparing maneuver envelopes, and, in the case of helicopters, this is all about the design of the main rotor hub. In general, one secret of long life in helicopters is to keep the main rotor always positively loaded, that is, to avoid low-G maneuvers. A rarefied elite of military helicopters like this Apache, displayed here by the British Army Air Corps, do permit some maneuvers involving low load factors, perhaps down to minus 0.5 G at higher airspeeds. This MBB-105 is another rare example. Its hingeless fiberglass blades and rigid titanium rotor hub can tolerate as low as minus 1 G. But our ride today is a light helicopter whose mission does not typically involve dodging enemy fire, but it does require low complexity and low operating costs. So it has a two-bladed, semi-rigid rotor system, which, unlike fully articulated rotor heads, does not allow the blades to flap individually. Instead, it compensates for the lift asymmetry on the advancing and retreating side by allowing the two blades to teeter as one, with a pair of hinges allowing them to cone symmetrically under positive rotor disc loads. This is a rather simple and compact design, unlike that of helicopters with 3 degrees of freedom blades, with individual flapping, feathering and lead lag hinges. But there is a disadvantage. Two-bladed teetering systems like this can cause extra problems in a low-G situation, the risk being that the sudden departure in roll associated with unloading a rotor is countered by the pilot with a big cyclic input against that roll, which might cause the blade pair to teeter into its own mast. So the words "low-G pushovers prohibited" are vigorously emphasized to Robinson pilots at every opportunity. Another interesting limitation of these VTOL machines becomes apparent immediately as we lift. Whilst we don't require a runway per se, we do sort of need a clear acceleration path ahead, staying close to the ground until we reach around 60 knots indicated, at which point we can begin to climb out of our hover takeoff run. This is in some ways akin to a multi-engine fixed-wing takeoff decision speed. We are essentially sneaking through between two "there be dragons there" areas on the helicopter's height velocity diagram, related to the possibility of an engine failure at takeoff. The skids could just about absorb most of the energy of a sub-50 knot, sub-8 foot power loss. Climb any higher than that in the first phase of the departure at low airspeed, and the sum of the kinetic and potential energy and main rotor inertia are not sufficient for a successful auto-rotation to a soft landing. Carry on accelerating past 60 knots indicated at low altitude, and the pilot might not have time to flare for a soft landing in case of an engine failure, or might strike the tail boom in the flare, hence the other prohibited area there on the right. Obviously, having a second engine, like this Airbus H135 does, makes a big difference, allowing this type of genuinely vertical takeoff, because in case of an engine failure you can expect a partially powered descent, likely dipping into some turbine temperature limit exceeding reserve power on the remaining engine as well, so more than half of takeoff power at your disposal. As opposed to the dead stick auto-rotation and the potential for a very bad day you'd find yourself contemplating for a short but very lively period of time in a single-engine helicopter. That said, such is the reliability of gas turbines today that some argue that single-turbine helicopters, such as the R66 and the upcoming R88, are perfectly suitable for these sorts of air ambulance operations that may require a properly vertical takeoff in an obstacle-rich environment. Back to 7 decades of turbine technology ago, for similar reasons, the first few seconds after liftoff were a rather vulnerable part of the mission profile of a tail-sitting fixed-wing VTOL aircraft as well, which is why the Lockheed XFV-1 had 2 engines buried in its fuselage, driving a common gearbox, and its liftoff profile involved an aggressive transition into wing-borne flight, starting to pitch down almost immediately after liftoff at about 5 degrees per second, thus also clearing the vessel and reducing the risk of a fully fueled XFV-1 falling back on the launch pad in case of total power loss. Of course, even partial power loss would have been an unprepossessing sight, as the thrust would have been marginal in terms of arresting the descent to the point where the pilot would have had a chance to position the aircraft for reversing onto the deck for a safe touchdown. That said, the pilot of the XFV-1 would have been sitting in an ejection seat, a luxury generally not afforded to helicopter pilots. Back to our 270 horsepower single turbine helicopter, and let us talk power related limitations. The power output of the engine is consumed in 4 main ways. First, the induced power related to the process of the blades generating lift, much like the induced drag power of fixed wing aircraft, is high at low speeds, it peaks in the hover and then decays in forward flight. Conversely, the power required to turn the blades against their profile drag increases somewhat with speed, sometimes to the point of necessitating swept blade tips on faster helicopters to decrease the leading edge normal Mach number on the advancing blade, delaying the compressibility-related drag rise. The third major component is referred to as parasite power because it is the speed times the parasitic drag of the helicopter, that is the drag of all non-lifting components, like the cabin. As this goes with the cube of the forward airspeed, it is where most of the power budget is spent at high speeds. And finally, the tail rotor and the electrical generators also consume some of the power. I'll call this power sink miscellaneous. So, the resulting total power required takes up a sort of bucket shape like that's seen in fixed-wing flight, the minimum of which gives us something close to the best endurance speed, somewhere between 60 and 70 knots on the R66. The ratio of power required to speed is important as well, because its minimum tells us approximately the best range speed, around 100 knots on the Robinson. The slope of a line from the origin to the power curve is, of course, this very ratio. So power to speed is at its minimum where such a line is tangent to the curve. Wherever the power required curve intersects the power available, we will have the power limited maximum cruise speed of the helicopter. This is around 135 knots in the Robinson with the 270 horsepower at sea level Rolls-Royce 300. I emphasized power limited there because other things might limit the speed too, for example, retreating blade tip stall. So what happens when we equip a fixed-wing prop of similar maximum takeoff weight with the same amount of power as the D-rated Rolls-Royce 300 in the Robinson? Fortunately, this need not be a mere thought experiment, because at least one such aeroplane does exist, and it is here, waiting for us at the National Flying Laboratory Centre at Cranfield University, along with pilot and long-time kind supporter of these design deep dives, Joe Brown, purveyor on his normal working days of precision flight test maneuvers on a 13-ton airliner. The shiny Part 23 aerobatic trainer he'll be flying today, parked on the Cranfield apron, is a Slingsby T67 Firefly, a type that served formerly as the RAF's elementary trainer. It is powered by a 6-cylinder Lycoming 540, super conveniently for our comparison rated at 260 horsepower, almost the same as the helicopter's total power. The Lycoming Flat 6 of the Slingsby turns a 3-bladed 1.75 meter diameter prop at a top speed of 2,700 rpm, about 6.5 times the rotation speed of the Robinson's main rotor. The tip Mach number of the T67's prop is higher too, at around 0.73, versus the Robinson's 0.64 at zero airspeed. The limiting factor for the latter was presumably the desire to keep the advancing blade below Mach 0.8 or so in a 100-knot cruise, 0.8 being roughly what you'd expect the blade's drag divergence Mach number to be. That is where the profile power of the main rotor would begin to run away from you. So to understand tail-sitting VTOL power requirements, we need to know how much thrust can the Slingsby generate at maximum power when the aircraft is stationary. The ultimate question being, if we sat the aircraft on its tail, much like the Lockheed XFV-1 was meant to take off, would it be able to lift off at full power like the Robinson can, equipped with roughly the same amount of power? A can-do attitude is built into the DNA of the National Flying Laboratory Centre, but a practical demonstration of the use of the Firefly as a VTOL tail-sitter would probably be unwise, so we'll take a more theoretical approach here to calculating its maximum sea-level static thrust.
The quickest way to come up with a back-of-the-envelope estimate of this is via basic actuator disk theory, which assumes the useful fiction that the propeller is a thin disk with a uniform velocity tube of air, or bundle of streamlines if you like, moving through it at some velocity Vd at a constant mass flow rate m dot, or dm over dt. Upstream, this same mass flow rate will come through a larger area at a lower speed. We'll call this free stream velocity v0. Downstream, the flow accelerated by the propeller disk will put that mass flow rate through a smaller area at a higher wake velocity we will call v1. The thrust is the rate of change of momentum along the stream tube, i.e. the change of velocity from upstream to downstream times the mass flow rate through the tube, which can also be written as density times the velocity across the prop disk times the area of the prop disk. We next apply the conservation of energy along the stream tube in the form we know as Bernoulli's principle, which tells us that the total pressure is constant in the part of the tube that is upstream of the propeller, as well as in the part that is downstream of the propeller, ignoring viscous forces, of course, with a pressure jump from PD minus upstream to PD plus downstream caused by the engine shaft power P turning the propeller. The thrust T is basically this pressure difference times the disk area. Subtracting the two Bernoulli equations from one another gives us the pressure difference in terms of the free stream and wake velocities squared. Equating this conservation of energy expression of thrust with the momentum one from earlier gives us one of the rather neat little results of actuator disk theory, namely that the flow velocity across the disk is simply the average of the free stream and wake velocities. Now, this is only as true as the inviscid and incompressible flow assumption underlying all this logic is, but it is an elegant little approximation. After a bit of manipulation of the two different thrust expressions, which in the interest of expediency I'm skipping here, and setting the free stream velocity v0 to 0, since we are interested in the static thrust case here, the bottom line is that the thrust generated by an engine putting an amount P of power into turning the propeller looks like this. Now, real propellers do have compressibility and viscous effects going on. Just about every variable does vary across the disk. The spinner reduces the effective area of the disk. No propeller turns all of the engine's power into thrust, especially not when the free stream velocity is 0, and so on. So we need to decorate the equation with some fudge factors accounting for some of the shortcuts we've taken in this analysis. I've estimated these from fitting this equation to a few known test cases. If we put some numbers into this equation, we get a peak static thrust value for the Slingsby of about 4 kilonewtons, or just over 900 pounds force, which gives us a maximum static thrust-to-weight ratio estimate of around 0.37, with Joe and myself and some fuel on board. This being less than 1 means that a T67 raised nose straight up on a helipad with full power set would basically have the same exact climb rate as the Angel of the North. It is not close to being able to lift either. The result would be the same even if Joe ejected me and most of the fuel from the aeroplane. This is, of course, not much of a surprise. A 1.7 meter diameter propeller spinning at 2700 RPM is a much less efficient peak thrust generating machine than a 10 meter diameter helicopter main rotor turning at a little over 400 RPM, mainly because the former needs to accelerate the air to a much higher speed for the same total thrust, and the energy required for this goes with the square of the wake velocity. Our conventional takeoff today should allow us to double check the static thrust figure we just came up with. We just need a basic Newton's second law model of the ground roll. Acceleration equals the sum of all forces acting on the aeroplane, thrust, drag and the rolling resistance of the wheels, divided by its mass. Inconveniently, this second-order differential equation is quite hard to solve because almost everything varies with time during the ground roll. But we just want a quick sanity check here, so I will simplify things drastically in a minute. But if anyone is interested in how to do it properly, I was sufficiently bored in the first COVID lockdown to work out a much more accurate model, taking into account all sorts of variations and interconnections between the various terms of the equation, as well as the fact that any attempt at validating the solution must account for the uncertainties in all the variables, such as where the aeroplane actually is at any given point during the ground roll. Perhaps the most interesting revelation from a model like this, as well as from the experimental data, is that all the time domain variations result in a non-uniform acceleration, as seen here for a larger transport aircraft. I've painted the acceleration as a color onto the runway to visualize this. But once we are just about rolling, assuming a uniform acceleration through the ground roll is not too bad. So that is exactly what I will do here for this quick sanity check of the thrust calculation. That means the acceleration in the moment after we start rolling can be approximated as the static thrust estimate minus a rolling resistance estimate using a μr of 0.02 divided by the total weight, which gives us 3.46 meters per second squared, or 6.73 knots ground speed per second. This gives us a 0 to 60 knot time of 8.9 seconds, and because we had almost no wind, we can look for those 60 knots on the airspeed indicator, at which time a stopwatch started when we began our rollout should be showing around 9 seconds if our 4 kilonewton thrust estimate is okay.
You happy? Happy. Okay, in that case then we'll add power. We'll add more and more power until we get to full power, keeping it straight down the centre line using our feet. A little bit of wind-to-wind aileron to the right. As the aircraft accelerates through 60 knots, I can increase our angle of attack, and we're airborne. We'll climb away initially 80 knots.
105, runway 21, wind 270 degrees and 9 knots, stay touch and go.
Trim the aeroplane out. And as we pass through 200 feet, we can reduce our flap setting now. They've done their job. Flaps are up. And we can let the aircraft accelerate through 90 knots up to 100 knots for its en route cruise climb.
Particularly astute viewers will have noted that the 60 knots indicated at which Joe rotated was exactly the same speed at which the Robinson's height velocity diagram had us transition into the climb in the identically powered helicopter. And it took roughly the same time to get there as well, perhaps slightly less by way of ground distance, and obviously in the helicopter we cleared a fence and some vegetation in the process, which would have been something of an inconvenience in the Slingsby.
22.855, aeronaut 02, yeah.
As we approach our cruising altitude, it is time to be compensated for the inconvenience of having required a runway to take off, unlike in the Robinson. The comparative fuel burn figures between the two equally powered aircraft tell us just how much more of that power is used up by the helicopter for the production of lift. In a range of, say, 100 to 110 knots indicated, we are burning of the order of 30 litres an hour in the Slingsby. An imaginary R66 flying alongside us would be burning a little under 90 litres of Jet A per hour. Granted, some of the difference is down to the R66 being powered by a gas turbine. They tend not to be all that efficient at this scale. So perhaps the more realistic comparison would be with a Robinson R44, powered by a different version of the same Lycoming 540 piston engine we have in the Slingsby. But even that would be burning around twice the Slingsby's fuel to keep up with us due to the inherently big difference between the induced power of the helicopter and the induced drag power of the fixed-wing aircraft. The fixed-wing aircraft is faster as well in terms of maximum cruise speed, but at this point the induced drag contribution is quite low in the case of both, so the parasitic drag power takes over, being perhaps a little higher on the R66 due mostly to its skids and its much larger cabin. We touched earlier upon the flight envelope limitations of the R66 and of rotary wing aircraft in general. Unlike the Robinson, the fully aerobatic Slingsby has no particularly dire warnings placarded anywhere. And in fact, as Joe pulls us into a wind-up turn with the horizon approaching a tilt of about 75 degrees away from its more customary location, at 3.5 G we are still a very comfortable distance away from the edges of the VN diagram in both axes. In fact, the Slingsby's maneuvering speed of 140 knots is the VNE of the R66. Here we have another 40 knots in hand until we hit the Slingsby's VNE. The Slingsby is also quite comfortable, structurally speaking, in low G maneuvers, with plenty of margin to play with on the lower half of the VN diagram, though I must admit to being closer at this point to the limits of the VN diagram of the cake I'd had for lunch.
And that's our students. Alright, so we'll take the power away.
As we head back to Cranfield Airport surrounded by lots of lush and green Bedfordshire, Joe flies an approach simulating the Space Shuttle's famous heading alignment cone descent path. Because of course he does. And since the Earth is coming up to meet us, it is perhaps a good time to think about dead stick emergency landings as well. The Slingsby has a best glide ratio of about 8 or 9 to 1, though of course this is heavily dependent on the type of engine failure and what the prop is doing, windmilling, feathered or stopped at some other pitch angle. By comparison, the Robinson has a best glide ratio of between about 4 and 5.5 to 1, depending on the auto-rotation speed.
So let us circle back to the XFV-1's power plant. We have seen that the same power that gets the R66 into the air comes nowhere near tail-sitting VTOL performance on the Slingsby, and very few fixed-wing props have the static thrust to takeoff weight ratio required for vertical liftoff. In fact, let's see what happens if we run some more numbers through the actuator disk theory model derived earlier, using the same efficiency fudge factors as I used for the Slingsby, which gave us 0.37, and I'm including the R66 as well, which comes in at a static thrust to max takeoff weight ratio of 1.12. With only 3 of us on board for the flight we saw earlier, the figure would have been closer to 1.3, I think. Some other fixed wing props, the Beech T6 Texan II, the aircraft military pilot trainee would fly before moving on to fast jets, I'm estimating at around 0.53, with its PT6 derated to 1100 shaft horsepower and assuming 10% of additional jet thrust. High-performance aerobatic aircraft get close to 0.8 or so. Their pilots sometimes fly maneuvers that look like they are just hanging off their props, but in most cases these maneuvers are transient and involve a little bit of height loss that may not be obvious from the ground. Which rather puts the challenge of the XFV-1 into perspective, considering that it also had a weapons payload to lift. Now, it is difficult to find reliable numbers here, but the Navy's Standard Aircraft Characteristics data sheet issued in October 1952 for the XFV-1 has the takeoff power of the XD-40 engine pair estimated at 6,825 shaft horsepower, with an additional jet thrust component estimated at the time at 1,685 pounds. If I plug these into the actuator disk equation, I get just over 76 kN of static thrust, which at a takeoff weight of 5.8 tons works out to a thrust-to-weight ratio of around 1.34. We have liftoff. Except, in the end, we did not. The XFV-1 did get into the air in the summer of 1954, but it was from a rolling takeoff using a sort of temporary landing gear. A few dozen test flights were conducted in this fashion at Edwards Air Force Base, and in the end the program was cancelled before a vertical takeoff could be attempted, though some now public domain reports suggest that the aircraft did successfully transition into a hover at altitude on one occasion. There was a more powerful version of the Allison turboprop in the plans, but it never materialized. By this stage, the summer of 1955, the world was looking to turbojets as the future of military aviation, and the interest in propeller-driven fighters was simply no longer strong enough to warrant the huge development costs ahead on either the Lockheed or the Convair design. It did not help that there were some significant technological risks around the development of a hover auto-stabilization system meant to help the pilot land on a ship deck with a very limited view of what was going on down below, with extra excitement guaranteed on a gusty day. There were a few more attempts at the tail-sitter idea. For example, the Ryan X-13 Vertijet got to the flying prototype stage a couple of years later, but the appetite for the concept was largely gone. And in the 7 decades that have passed, no tail-sitting convoy fighter ever materialized. When needed, destroyer escorts provide air defense to commercial shipping. The advent of efficient turbofans brought us amazing fighters capable of hover and vertical landing, most notably the Rolls-Royce Pegasus-powered Harrier. But since their takeoff jet blast would be unhealthy for most ships, they still need a runway. Lockheed didn't completely let go of the fast, agile VTOL idea, the result in the late 60s being the Cheyenne compound helicopter, with a short fixed wing and a pusher propeller. Sikorsky also developed a compound helicopter, the S-67, and Boeing built a sort of Chinook with wings, the BV-347. But none of these aircraft made it into production. The compound helicopter allows higher load factor turns because the wing takes up some of the load, and the thrust of the pusher prop is useful when the speed is power limited and not retreating blade tip stall limited. But once again, there is no free lunch here. The wing generates a download in the hover and it blanks some of the rotor disc in auto rotation, which ultimately reduces main rotor RPM, and that is not good. So today, the helipads of ships are still mostly used by conventional helicopters. They are not that much faster than they were in the 1950s, but they are so versatile and capable of operations that the likes of the XFV-1 would probably never have been able to accomplish, especially lifting heavy things, precision winching and so on, all without requiring any sort of ground equipment. The fashionable solution to the fast and efficient VTOL requirement is the transitioning variable geometry aircraft. The poster child of the idea is, of course, the Bell Boeing V-22 Osprey tilt rotor, and this is the direction in which much of the commercial electric VTOL industry is going as well. But variable geometry means increased complexity, part count, weight, and exotic failure modes, plus potentially lengthy certification. An example is the turbine-powered and V-22-inspired Leonardo AW609, undergoing certification flight testing, in development for over 25 years now. 7 decades after the XFV-1, the tail-sitting VTOL concept still appears to be the cleanest, most efficient and least complex route to VTOL. The main problem with the XFV-1 was the landing, placing exceptional skill requirements on the pilot, but with modern digital control systems, this could be dealt with quite easily nowadays. Here is a little prototype drone developed by our aeronautics and astronautics students here at the University of Southampton, capable of accomplishing that very task. So, why do we not have tail-sitting electric VTOL aircraft in development? Well, yes, I do realize that the average air taxi passenger does not particularly like being tilted by 90 degrees as the aircraft pitches into its cruise attitude. But is this not solvable with some clever cabin design trick? The US Office of Naval Research used to have a vessel called FLIP, which, rather amazingly, could be operated in both horizontal and vertical orientation. It even had bathrooms that worked both ways, including the sink. The XFV-1 had a pilot seat that could tilt forward by a few degrees when landing, giving the pilot a fighting chance to actually see something down below. Could passenger seats tilt, a bit like on a Ferris wheel? Or perhaps cargo transport is the low-hanging fruit here. Of course, as we have seen, the power-to-weight ratio required for takeoff and landing is larger even than on most aerobatic competition aircraft. So the only missions where this would make sense are those where speed is more important than range. Is that a large enough niche to warrant an experiment? I do hope to see a tail-sitting eVTOL passenger aircraft at some point. If nothing else, entertainment would be guaranteed.